Hi, welcome back, everybody. And we almost reached the finale. And now, this lecture video, we are talking about section 10.4, the exponential functions. And during this coronavirus period, I think one of the things you heard a lot from the media is they all talk about the exponential functions, right? They said the new cases and the number of the deaths, those things like they follow the exponential functions. And in fact, there were so many different models was developed and try to estimate when is the turning points, those things. So now we got a chance to get exposed to what is the exponential functions. So that is kind of like excited to learn about it. So in fact, if you look at those, a lot of people doing the model for the coronavirus, so they use the exponential function, but really the functions, they were doing the modeling is we call it logistic. So what I mean the logistic is kind of like the function, the initial stages, right? So this just a sidetrack about a little bit. So in the initial stages here, you have the exponential growth, like we all talk about, your number of cases increase, right? So the logistic, the real exponential function will continue to grow, but the logistic is like after you have the exponential growth to a certain period of time, then it will start to turn, and then they will plateau out. Okay, so this is the point. We call it is the turning point. So like in here, the previous, these ones here, right? Before that, this is the exponential, right? So they grow pretty fast. So it's a concave up. And then after they turn in this point here, right? So they get the peak and then the curve bend. So the whole this function, we call it logistic. And the logistic function is a function pretty good on the estimate, like the population growth and the virus growth, those things, because they're going to plateau out. So I think, this turning point here, I think in the US right now, we are looking like Texas, I think we are looking around like the April, 27, of course, the model constant judge, the changes here. So like in the US, some like the big cities they already reached this point. Then they start to kind of go into the second stage of the logistic functions here. That's why they were thinking about maybe we can opening some business, but be very careful doing that. So that's one very interesting applications. So next time, when you look at those news, look at those data, you will know what is exponential. So the exponential from the logistic, they are only look at the first part. Yeah, when the virus first start, the spread of the virus does follow the exponential. But then when we have like the social distance and the different actions, then they're going to reach this turning point, and then the curve will bend. That's why we say with smooth curve, really, you're going, the key point is when is this turning points, right? Okay, anyway, this is the sidetrack about, what we learn in the math. A lot of students say, oh, I need to learn math, I never use it. In fact, you do, right? So especially in this one, so many people, they reporting the different models. They are all based on the, the mathematical functions here. Okay, so let's interested. Hope you find it very interesting. So what do you learn in the math? In fact, it has applications here. Okay, so let's take a look at the definitions. Okay, so the definition, the exponential function. So this, how do we define that this is y is equal to the ax here. Of course, here, the a, we have to be greater than 0, and the a is not equal to 1, right? Because if you have 1, that means can be any powers here. So this number, excuse me. So this number is here. This is what we call is the base. And this numbers x here, this is what we call the exponents. Okay, so this is what we call this exponents here. So y is equal to the ax here. And one very special one is we call this the one special exponential function. Is when the a equal to a very special, we call this the natural numbers, right? So what is the e's here? Remember that we talked about this before. E has a special value, is 2.71828. And this number we call it the natural number. The reason why we call it a natural number is because a lot in the in the nature, a lot of situation you can be described by these numbers here. So, but a can be anything, right? So one special function a is equal to the ex. This is, we call it the exponential function, and then in fact, the e was developed by a statistician called Bernoulli, and so the way he find the E, and it's kind of like he's a businessman, right? So he's a calculated interest. So he's trying to find a compound interest. We learned the compound interest concept, right? We use the PERT things. Do you remember that in the other chapter? So that's why he said when you continuous compounding, you're not going to get the infinity number of the amount of the money. They're going to plateau out, right? So that's what is the E functions here. But anyway, so that is a special. So so that is a special function. So you will have y is equal to the ex, and this is the, this is the one. This is the most very, very commonly used, right? So this is a commonly used exponential function. So this is the most commonly used exponential function. But of course, we can change the base to different things here. So let's take a look at in general the graphs of the graphs of the exponential function. Okay, so in here, if your base, okay, so if a is greater than 1, okay, when the a is greater than 1, then your exponential functions going to grow like this. So it's increasing, right? So that's how fast like we talk about in the various situations, like how fast you double that. So, the E is 2. So that means when the A is greater than 1, you are kind of continue to going up. That's what we said, exponential growth here. Then here for the exponential functions here, we always have one very, very key point. This is the point that will help you to graph. So this is the point is when x equal to 0, y equal to 1 is here. Okay, so like then the same things here. Let's take a look here. So okay, so the another ones here, this is what we call is the, when this is the one when, oops, this is the one when the a is less than 1. So what is this graph looks like? This graph looks like this. Of course, this is a curve, right? Okay. So this graph is look like this. Of course, here we also have a key things here. This is 0, 1 again, right? So, you know, when a less than 1, this is we call it exponential. So for these situations here, we call this is the exponential decay, right? So for these situations here, we call this is exponential increase. I don't know you guys remember or not, like a few years ago, I think in the Russian has a nuclear, I think the electricity manufacturing place, the nuclear, I think the oven burned down and then the like radiations start leaking out. And we know the radiations in the natural environment, it will gradually decrease, right? So that's why for the, the nuclear radiation, when they decrease, that's why they will follow the exponential model as well, but they will follow is a decay model. That means over the time, they will drop, the radiations in the air will continue to drop here, right? So that's what we call this a decays. That means your decreases here. Okay, so now let's take a look at some examples here. This section, in fact, is a pretty easy sections, right? So now if I said I want to, let's take a look here. Okay, so if I want to graph, okay, so let's take a look. So if I want to graph f of x equal to 3x here, right? Okay, so let's take a look here. So this is kind of back to what we learned for the, okay, so for the 3x, remember, right? So remember that we said the key points here is 0, 1, 1, 2, 3, 4, 5, 1, 2, 3, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. Okay, so the original functions here, right? So we know the key points here is this 0, 1 point, right? Okay, then when the x equal to, x equal to 1, you got a 3 here. X equal to -1, you got a 1/3 here, right? So this is what is the functions looks like. Right, so this is what is the exponential function looks like. Gee, I really just, hate this. It's just terrible, this drawing. And really, so this 1/3 here, so I don't know. Okay, well, now if I want to do like f of x is equal to 3 times 3x here. Okay, so for the 3 times 3x, right? So it's really, this is 3, the x plus 1, because you times it, you kind of equal to, you add the exponent, so 3 times x1. Then from the transformations, correct? So I can use this as my base function. So what does that mean? That means I move to where? I move to the left 1 unit, right? The reason why I move to the left, because I set this one equal to 0, so x to the -1. So that means I'm moving to the left, right? So here, take a look. So this is what I'm going to use. This is use the purple, right? So this is the purple color, or pink, you can call it. So that means move to the left. So this key point going to move to here, right? And then this key point going to, so like for -2 going to move to here. So this is 1, there's 3. So the 1, I'm going to move to 0. So I'm moving to the what? I'm moving to the left. So by using the transformation, I can know this is my key, this is my functions, right? Okay. So like the same way, so if I want to, so from the same way, so if I want to do the f of x is equal to 3 to the x minus 1. Then what happens here? I know what happened here. So this one I set equal to 0, x equal to 1. So I know this one going to do what? This going to move to the right, right? So this will move to the right 1 unit. So let's try to graph again. So that means this point going to move to here. Then this point, right? So this point was original point is negative 1, 1/3. This point going to move to here. Then the 1 going to be moved to 2, so going to move to here, right? So then that's what is your exponential function going to looks like, right? So just remember, right? So if you find the key point, then that's where you can use it, to kind of guide you, then by use the transformation to guide you to do the graphs here. Then the next thing here is also pretty easy. Let's take a look. How do I solve for the exponential functions here? So for the exponential function, we have one very good property. Okay, so if the ax is equal to ay, then you can conclude x equal to y here, right? Because if the exponential function, they have the same base, right? So the base here is both a, so it's kind of, you can just remove that and then solve for that. Okay, so now let's use these ones here, try to solve a few problems here, and this will be, in your homework. So this is like a 2x equal to 32. So how do I do this? So I know if I change to the same base, so I know the 32 is here, right? So 32, I can change it to the 2 to the 5th power. Then here I have a 2 to the x. Now you say, hey, they are the same base. Okay, so the same base, you kind of can cancel that out. So what is your x value? X equal to 5. Okay, now let's take a look at the next ones here. Let's just need to be careful about it, right? So this is 3x equal to 1 over 81. So I know I need to change it to the same base. So let's start to work on the 81s here. So 81 is 3 to the how many power? 4th powers, right? And then we learned that it's exponential in the previous chapter. I think it's in the review sections. We learned in the beginning of the semester. If they are in the denominator, if you want to flip it, what you need to do? You put a negative, right? That's what the exponential things we have here, right? So let me write it here. This is kind of like the review, what we did for the exponential things, right? So we say, if ax times ay, then this will be equal to the 8x plus y, ax divided by ay, so this will be 8x minus y. So if x y, so this will be 8 to the xy's, right? Then one other thing we say negative x is equal to the 1 over x, or 1 over x, if you flip it, is equal to the negative x. So those are the things we learned previously. So let's just put it there so we can reference it back. Okay, so now I said 3 to the negative 4. I got what? I got the same base again, so I can cancel that one out. So what is my x values here? X value is negative 4 here, right? So that's what I can do that. Okay, so now let's take a look at number 3 here. Example number 3 here. So I have a 25 to the x is equal to 125. This one's here is x plus 2. So I know I need to change it to the same base. So my left-hand side, let's work with 25 is what? It's a 5 to the what? Second to the x. 125 is what? 5 to the what? 5 to the third, right? Then here, this is x plus 2. Okay, now I'm using these properties, right, to distribute it. So this will be 5 to the 2x. Then when I distribute these ones here, you need to use the distributed properties, right? So this one will give me 5 to the 3x plus 6. You see, the same base, you can cancel. So that's why the 2x is equal to the 3x plus 6. Okay, minus 3x minus 3x both sides. So the negative x equal to 6 divided by negative 1 divided by negative 1, x to the negative 6. That will be our solution. Okay, let's do it one more time. One last example here. Okay, so this one's here. This is e to the 3, right? So e to the 3 negative 2x is equal to e to the negative x plus 5. Okay, don't be freaking out to see the e. Just remember e is some number, is one of those irrational number, 2.7182, dot, 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 dot. So it's just kind of like the pi sim type of the things. So don't get freaking out, it's just numbers, right? So now I'm using the same thing, the same properties here to dealing with this one. So my left-hand side will be what? E to the what? Negative 6x. My right-hand side is e to the x plus 5. What did you see here? Same base. So you can cancel. So let's give you negative 6x equal to the negative x plus 5. Then plus x both sides. So you got a negative 5x equal to 5. Then divided by negative 5 divided by negative 5. So x equal to the negative 1. So here is the answers here. All right, so this is a pretty easy sections here, and I hope you enjoyed it, and I hope you enjoy hear the story about the exponential function and how in current situation we are in this coronavirus situation, how do people use that to estimate. So now you can tell people, say, yes, I learn math, and the math does have some application in the real life. All right, so that's pretty cool, right? Okay, so I guess we will stop here, and I hope you enjoyed this video. And I guess I will talk to you next time when we go to the, okay, so, okay. Okay, so sorry, a while ago, I just accidentally hit the stop sharing. But anyway, so, okay, so I guess the next time I will just see you, talk to you again. And so that we're going to cover the last section of this semester, section 10.4. We finally reach our finale. It's so nice to talk to you over the video. I hope you enjoyed it, okay? So don't forget to do the classwork and the homework, right? Okay, so I guess I will talk to you later, all right? And take care and be safe.